Hello everyone, and welcome to the Trends in Battery Technology panel discussion. Tonight's panel discussion is going to be chaired by Dr. Jacques Eksteen, who is the Chief Operating Officer and Research Director at the FBI CRC. I'm going to hand over to Jacques to look after the panel this evening. Thank you.
Thank you very much, Alison. Welcome everybody. I hope you enjoyed the conference thus far. We've got an interesting panel session in the next hour. How we will run through it is basically I'll introduce very quickly our panelists, and then subsequently we'll cover a few questions and then take questions from the audience. And please use the chat box function available to you to enter questions, and I will try and then note them and then ask the panelists their responses. Just running through our group of panelists, you would have their bios accessible. Nonetheless, I just want to quickly mention them by name and some of their affiliations. Firstly, we've got Dr. Adam Best. He's the Principal Research Scientist at CSIRO with a long history in lithium-ion batteries. Very specifically, he's also the co-chair of the International Meeting on Lithium Batteries, and the next one is to be hosted in Sydney in 2022. And he's also recently co-founded the Australian Battery Society. The next panelist is Professor Alexandre Chinas, and he's a professor at Université de Lorraine, associate also with the CNRS Geo Resources. Published extensively many papers and journals and books, and specifically he focuses on the technological barriers for the recovery of metals from primary and secondary resources. Andrew Mckenzie is our next panelist. He is the Managing Director of EnviroStream, with over 22 years of experience in industrial processing, recycling, and manufacturing experience. Currently, he's, as I say, the Managing Director of EnviroStream Australia in Victoria. Very active in the space of battery recycling specifically. Next on the panel is Professor Jose Alarco. Jose is with the Institute of Future Environments at the Queensland University of Technology, or QUT. Jose has been involved in research and development from laboratory to pilot scale on the production of superconductors, batteries, and various nanotechnology materials in both academic and commercial applications. You'll see the rest of the write-up, I guess, in the bios provided. Dr. Mado Shabani is a research fellow from Monash University. Mado is a energy storage researcher. She's an inventor and solution provider, and with a lot of expertise in material synthesis, engineering, and scale-up. Then Professor Marie Lundstrom. Marie is a professor in hydrometallurgy at ALTA University, with a strong focus on hydrometallurgy, corrosion, and then the circular economy of metals, battery recycling, and material efficiency. She's got a research group of about 20 to 30 members. And then Mike Vasey from Lithium Australia, who's also the head of battery materials. Mike is the head of battery materials at exploration technology company Lithium Australia, and the executive director responsible for leading the re-establishment and commercialization of nanotechnology and cathode powder technologies through the business, the Very Small Particle Company, or VSPC, and is the director of battery energy storage supplier Soluna Australia as well. Mike has got a bachelor in chemical engineering. So I think we've got a very diverse group here of panelists, and hopefully offering us, some insights across the battery value chain, and naturally within the context of ALTA, which is very much on the metals and materials side of things, but nonetheless, I would appreciate your insights. So we're going to start off with a few questions that we see here in trends in battery technology. Some is probably not a trend yet, but what we have seen, for instance, in the lithium industries is it's gone through a rough patch. When we started the Future Battery Industry CRC and with the bid process in 2018, lithium was actually at a high, the middle of 2018, and there've been a few transactions, and some companies bought into a lot of debt at the time, made a lot of debt too, and have been caught in difficult spots since then. We've had a few business failures at Nemaska in Canada and in North America, and also here in Australia recently, Altura, and we've noticed, that in a number of news releases that TNC Lithium has gone through a difficult patch. I'm not sure if that's been resolved yet. I would love to hear some of your thoughts about the situation in the lithium market, maybe if you got any insight in that space, and the companies that made it versus the companies that didn't. If you've got any feeling for those that are actually, was it an issue of just the debt equity ratio? Was it about offtake? So I'll maybe ask a few of these panelists, and then we'll move on to the next topic. And I'll take questions from the audience. Please use your chat box for that, and I'll try and attend to those. Mike, if I can maybe start with you, just some thoughts on just the nature of where the industry is at the moment, and do we have hope for the future in the first place? I think in the lithium industry, looking at next year and the years ahead. And what are your thoughts on this?
I definitely have hope, Jacques. It has been a tough couple of years for the industry, but fortunately there are some green shoots, definitely. I guess from our observation, things got difficult early last year, and one of the things that transpired was the Chinese government policy changed their rules around subsidies for EVs. I think that was May of 2019, and their policies prior to that had been driving the industry towards energy density. Well, that was the prime motivation from what we could see. And I think they realised that other things were important as well, safety, cost and performance. So they changed their rules in May last year related to subsidies for EVs. And from what I see, it sent a shockwave through the whole supply chain in industry in China. So EV sales slowed up, and then there was a credit squeeze through the whole supply chain, and there's been a shakeout. The smaller, more expensive producers, perhaps using older technology or running at higher costs, being squeezed out. And that's taken a year or so to sort itself out, and it's still ongoing. That said, I think there's no doubt the EV industry is on a growth trajectory. We're looking at 5 to 10-fold growth rates over this decade in terms of volume. And we're starting to see interesting developments in the battery platforms with sort of the re-emergence of LFP, which is a subject very close to BSPC and Lithium Australia, and a realignment of priorities, I guess, in terms of battery technology.
Yeah. Adam, some of your thoughts maybe, if you're
Yeah, thanks, Jacques. I think I'd agree with Mike that definitely the changes that the Chinese government made were quite substantial at the time, and also, as Mike indicated, there were quite a number of very small state-owned enterprise battery companies that were dotted all out throughout pretty much nearly every Chinese province, and the government made those decisions not to continue to subsidize and support those companies. So that has led to that shakeout that's occurred. So that has definitely had an impact. So that's also obviously deals with the supply side of the demand for lithium. So I think that's really has seen the impact. And as you indicated earlier, when you started the FBI CRC, everyone thought that spodumene was going to be the new iron ore gold of Australia. But as we've seen now, it's pretty cheap to go and buy spodumene. Anyone who looks at the S&P Platts and any of those markets will tell you that spodumene's pretty cheap at the moment. So that's definitely putting a lot of companies under the squeeze. But for how long that will occur, it depends on who you listen to. But it's definitely going to be through to at least the first quarter of next year. Before they're expecting to see a recovery in the demand and also in the price. But again, as has been noted with the COVID recovery plans of many governments around the world, it's also being tied very much strongly to clean energy. And I think that's going to see a significant boost in the demand for lithium and lithium products. So I think the other learnings I think we can also see should be also, we don't have to look too far back to see the Clean Energy Act that the Obama administration ran in 2008, where they tipped a huge number of subsidies into the US market and tried to spur battery growth. And there was a very strong boom-bust cycle at that time where the demand curves just did not meet the actual real expectations. And so a lot of companies felt the pain at that time. So whether this time we're going to see another one of those, it's not yet clear. I'm a big believer that predictions of these things is almost like a crystal ball. Depending on how many times you shake it, you might get a different answer, because it really depends on the demand and subsidies and the competitive costs of these products in order that people will actually buy the end product, which actually drives the raw material demands. But I think in Australia, there's a lot to be excited about with all the activity going on, and hopefully some of this material actually be part of our sovereign capability as we move forward in the years ahead.
Thanks. Marie, just on your side, it would be great to hear a bit of a European view and out of Finland. Firstly, I'm not sure how lithium is mineralized in Finland or in Germany. Is it a lepidolite or a spodumene or a different source? I know there's not huge resources, but how do you see your European supply? And where would you get it from, and what's the nature of your internal resources there?
Well, that is actually a very big question in Europe at the moment. We don't have so much of primary resources. One of the biggest resources, spodumene type, is in Keliber area in Finland. About 95% of Finnish known resources are located there. And it has been evaluated that maybe there could be 3 times more, but it's still not huge. And therefore, the recovery of lithium from recycled batteries is of high importance and interest, and also recognized in European R&D strategy with the battery raw materials. Lithium is not easy to recover from the recycled batteries either. So far it has been mostly lost, but there is more and more innovations and totally focused recycling plants for battery waste which aim to recover or do recover lithium. But let's say that compared to the discussions in Australia, so the discussions in Europe are very of the different nature.
Okay. Do we, Andrew, and just maybe to Andrew Mckenzie, Andrew, your experience in terms of is EnviroStream actually looking at recovering the lithium as well? I know there you've got the usual valuable components being nickel and cobalt, but if you look at the total cell with copper and aluminium and the foils, the nickel, cobalt, manganese, and lithium being both in the electrolyte and in the cathode, just what do you see as the option to recover lithium? Is that a reality, or is that something that at the moment is not really a strong area of focus?
So it's a strong area of focus. It's just a difficult area. With the biggest problem we have is the volume. I think when we look at the expense to do that activity, you have to look at the higher percentages of the battery, and the issue is that with lithium being a low percentage, it's difficult to justify. That's the reality. So it's a focus, and it has been a focus of what the work we've done and with VSPC and with Lithium Australia to get lithium in a phosphate state to be reused has been a great outcome. But when you look at putting the plant in, you kind of go, well, that's not so good. But so the focus really at the moment is to collect more batteries. To hear Murray speaking about how important that is, I think Australia needs to look at that as a critical supply of this material, and hopefully that's what we start to see happen, because that's our issue, is we've got to get enough volume to make these plants viable.
Yeah. Okay.
Right.
Yeah. Well, I mean, it makes totally sense. Thanks. And just see, Mado, you just joined. I think you've actually been you've also presenting for another session. So welcome.
Thank you. Yeah, I sincerely apologize for running late. I faced an ironic overlap. Yeah,
okay.
with another conference.
No worries, Al. And Alessandro, I just want to check with you with in terms of in France, if you look at the supply chains of lithium into France for companies such as Saft Battery and others, what's the supply chain? Where does France actually source its lithium from?
Okay. Then today, most of the lithium is provided by South countries, South America countries, and the supply chain is not so easy because it is as we know, in Europe we do not have many lithium resources, and mining is a little bit tricky. For instance, we have in Portugal. We have a deposit, a lithium deposit, but okay. In the past, we were mining countries in France, or for instance, but today, and in many other countries, European countries, but today we are not really mining countries, and we have a big issue that we have to take into account very early if we want to supply lithium from primary resources, is the social acceptability. For instance, in Portugal, the main problem is that we have to explain to the population that they have to accept mining in their region. And that's our big problem. It's not the same in mining countries like Australia, for instance, or Canada, because they have for many years, and they have never stopped mining industries. For us, it is really the big issue, and it's a big issue for lithium supply, even if we have several lithium deposits. In France, we have one Mckenzie deposit exploited by Imerys, which contain a little bit of lithium, but today the concentration is not very high, and it's also difficult for us. Then that's why in European countries, and more especially in France, we are very interested by the recovery of metals, including lithium, from spent lithium-ion batteries. Today, most of the processes are relies on pyrometallurgical processes, and in these processes, lithium is not recovered. It's going in the slags. That's why it's important to go to hydrometallurgical processes. We have several industries in France which are interested by the development of such processes, like Eramet, for instance, or Orano, or Solvay. But the main problem today is that we don't have enough lithium-ion batteries, and then we will have these batteries in 10 or 12 years. Because 5 years ago we said, okay, spent lithium-ion batteries will come back. Spent lithium-ion batteries will come back in 5 years. Now the lifespan has increased. It means that we will have to wait for 10 or 12 years. Then it means that first, if we want to develop this industry, we will have to process scrap of lithium-ion batteries production. And then it's not so easy to have investment on this technology. Then today, Europe is doing many efforts to start collaborative projects between industries and academics, between industries involved in extractive metallurgy and industries involved in production of lithium and batteries. But it's not so easy to organize. It takes a lot of time. Then recently we have implemented a new institute, which is the European Institute of Lithium. And the goal of such a kind of institute is to help to have a systemic and holistic overview of the value chain to get the best, the optimization of the supply.
Thank you. Thank you very much. I just want to move on to the next question. We are just on the next thing is on lithium refining. And I think one of the things is to say, well, you know, currently the conventional lithium refining is a fairly energy intensive process. It is particularly from hard rock. The typical raw materials is out of Australia would be spodumene, out of China would be lepidolite, and out of South America would be your lithium bearing brines. If we look at these opportunities, I'm just going to ask a few to maybe respond as to how we can, what would you view as the high impact improvements that we can maybe look at for yield improvement, waste reduction, and improving energy efficiency? I'll give it maybe start this time with Adam, if you don't mind, if you've got a few ideas, or if you don't, just say pass and I'll go on to the next person.
I'm probably a bit further downstream there, Jacques. I'm more interested in how you produce lithium metal. So I think this is, I'll leave this to the geologists and mineral processors.
Mike, have you got a feel for, you know, what you would think if you look at the current refining space for lithium? You know, what are the key areas that we can look at to really improve our refining? Just maybe three or four areas that you know of that might make a difference.
Yeah, this is a subject that Lithium Australia has spent a lot of time working on in the last few years. Probably the key point is diversifying the lithium product suite to include lithium phosphate from these conventional processes, whether that's a brine source or a hard rock spodumene source or some of the other sources. We think with producing lithium phosphate actually complements those processes, and it's just a feature of the chemistry and the solubilities of lithium carbonate versus lithium phosphate. As an example, lithium phosphate's a great product in terms of its quality that you can produce from these sort of streams, these leachate streams, and it can be done cost effectively, and with the sort of strong demand that will grow for LFP as one of the cathode material options. There's definitely a market there for lithium phosphate. Lithium phosphate can be used by some of the conventional processes for LFP manufacture, not all, but there's certainly an emerging and very strong demand in China at the moment for lithium phosphate, and I expect to see that demand move to the international markets as cell making grows in the non-China geographies. And lithium phosphate addresses some of the issues around energy efficiency and dealing with dilute lithium streams. The other area for potential improvement is the recovery of lithium that's lost in the fines and the sort of beneficiation of spodumene. There are technologies, and Lithium Australia has one to treat such material and again produce lithium phosphate from a hydromet circuit, and it's really the low solubility of the lithium phosphate that enables that to be cost effective.
Okay, Marie, if I might ask you, have you got at ALTA, have you done any work on lithium refining and maybe identified anything in this space, and if I would actually want to throw it open to all panelists. If you've got a idea in this space, just let me know, or just put your hand up, and I'll get you. So maybe just Marie, and then we'll follow on with anyone else that can respond.
Well, maybe I would in this stage highlight also the meaning of the impact of chemicals and energy used in production, because as mentioned, we don't have so much primary production in Europe. But when we look for example, the future caliber process, we have been doing work to model that beforehand and to calculate the life cycle impacts of future processing. And for example, already in this planning phase or designing phase of a new plant, so testing, for example, different chemical sources or energy sources, and which of those would result in the lowest CO2 equivalent, so actual impact for the environment. So maybe that is one of the aspects, for example, to be considered, that if a production is energy efficient, but if the energy is produced in a very CO2 heavy way, it might be totally different impact on environment compared to the, for example, less energy efficient, but if it's done in, let's say, Norway, Iceland, where is a lot of CO2 low energy usable. So the location also has an impact in addition to energy efficiency itself. And related to lithium recovery from the battery waste. So there we definitely have the challenge of losing lithium to side streams, like in primary production. So when we come to the process to the end of lithium recovery, in conventional sulfuric acid leaching process, we have lost already 30% to different side products or other products or neutralization residues. So this is one of the topics to focus in the development of recycling processes, that how do we address the lithium recovery more efficiently by the new innovations in processes.
Okay, thanks. Are there any other panelists who want to maybe just comment on this point before I move on to the next topic?
Maybe just quickly that it does affect, like, again, it does affect the whole, the cycle of the batteries. If we just used a pyrometallurgy process or anything, yeah, you've got to really look at the process at the back end as well. So to recover metals, we heard it just then, but at the same time, it's something to consider even at the recycling end for sure.
Okay, right, thanks Andrew. Next question that I would like to address is really around cathode materials, and we know there are a whole range. So we've got our LFP, and then a range of NMC, NMA, NCA, various chemistries that are out there. I guess here in Western Australia, with our nickel endowment, the question is, are we on the right pathway to explore the production of these high nickel ternary cathode chemistries? So, and to what extent are we backing the right horse, I guess is the question. So I guess what we've seen is that already the cobalt portion is already being thrifted out of our EV batteries. Definitely, I think the mobile phone and laptop batteries will still be, many of those would be the LCO, lithium cobalt oxide batteries for a while still, but for electric vehicles, which would be the largest use of at least there we see high nickel NCM, that's 811 and beyond, so higher than 80% nickel in the nickel manganese cobalt mix, going up to 90% even and beyond, but it brings its own challenges in terms of stability and so on. I guess the question is this still the area that we should be in? And I guess this is more a question for our Australian counterparts, although in Finland, for instance, in Harjavalta in Finland, BASF has worked with Nordnickel to set up, they're setting up a cathode precursor plant there, where that material is then, after making a mixed hydroxide, cathode precursor. They ship it to Schwarzheide in Germany to convert to lithiate and then convert into the cathode active material. We in Australia, for instance, at the FBI CRC are very active at the moment in looking at having a pilot facility for precursor and cathode active materials production. And naturally, we want to also make sure that we're backing the right horse. I know, Mike, within VSBC, the focus has been more on LFP for very specific reasons. And I think that's, but I guess this question specifically is more on the ternary high nickels. So maybe I'm going to put it open to anybody. So just maybe raise your hand if you want to comment, and I'll try and direct the question to you. Jose, yes.
Yeah. Well, the market research indicates that that's where the demand will continue. And the investments that are taking place, you would expect that there should be at least a buffer of years where there is some stability for the products in the nickel-rich composition. And the understanding of the material is improving also with the type of coatings stabilizing the surface. So I think the indication would be that it should be a good bet, at least for a good window of years. Maybe to add to that is the spider plots of the different characteristics that we want in a material in terms of cost, safety, that nickel-rich composition can reach a reasonably good balance. So, in my opinion, I think it's a reasonable bet to continue in this area.
Thanks. Adam, can I quickly ask you what's normally the problem if we get to nickels of 90% and beyond? What starts to happen? What problems do we start hitting when we're getting to those very high nickels?
Where should we start? Most of the biggest issue, as Jose has mentioned, is the need for cathode coatings, and this is due to the reactivity of the high nickel content with the electrolyte, because the high capacities that you're able to extract from these 811 and higher electrolytes, or higher cathode materials, you need to be going beyond 4.3, 4.4, 4.5 versus lithium plus. So you're very much in the oxidative window of the electrolyte, and disturbingly also at the current collector corrosion point as well. So you need to be thinking about how are you going to stabilize your electrolyte in order to be able to provide not only the cycle life but also the calendar life of the cell chemistry. And I'd absolutely agree with Jose that the companies now are making investments now that are going to be well and truly there for the next 12 years. And I don't see them being supplanted. Also, the economies of scale at work here are also driving the cost down below the $100 per watt hour per kilo, that the USD is set, and that's also another big driver, and that comes again from economies of scale. So the challenge actually is not really around the cathode materials. It's actually on poor people like myself as an electrolyte scientist to say, well, how are we going to design better electrolytes with the same physical properties as what we have in our current lithium-ion batteries that are going to be able to enable us to really take advantage of these 811 chemistries and even higher nickel chemistries, that we can even have even better performing devices. But obviously the other critical aspect is ensuring that we maintain safety.
Okay. Andrew, do you see any, how does the economics of recycling change with running very high nickels? Does that really make it a more profitable thing for you on the recycling side to be in?
As long as the mining companies don't get too organised and flood the market and lower the commodity values, we're always fine. So, but I think just quickly on it, the market analysis from our end on a waste that's arriving in 5 or 10 years' time, they're looking at what was built now and what's getting built, tomorrow, and it has still got a good nickel life. I think that's the thing. The energy storage market, I think, is the one to watch for the other alternative batteries. I think the car market, I don't know if people are comfortable with a 200-kilometre range. They do want higher ranges. They do want more energy density still. I think that car will sell at a higher value. the European market, the American market, the Australian market will demand those cars, and that's where those batteries will be. I think the energy storage is the alternate market, and it's really in its infancy, I think, still at this point from a recycling side. So, but just on that, really, if we've got lower nickel values or recovery rates for us, it does get underpinned by the stewardship, because it's one thing to process batteries, but it's always another thing to collect and get out there and go and get it. It's a big cost to our business, and that's where landfill bans and stewardships really help. But it's one thing to process, it's another thing to collect.
Yeah. Mado, I think between you and Alessandro, I just want to hear maybe from your side quickly your thoughts on I'm not sure if you're active in the space of cathode, cathode materials development, and in particular, what your vision is in terms of where you see cathodes, high performance cathodes would be going for, particularly for, let's say, electric vehicles and that.
Yeah, well, I'm actually not that active on the space of cathodes, but I totally agree with Adam. As long as we cannot see the improvements like in the current collector or in the electrolyte stability, it's going to be difficult to use those high voltage cathodes. But we are certainly going to need them, because at some point we're going to see higher fractions of silicon in the silicon graphite composite anodes, and then the limiting factor would be the capacity of the cathode. So we're going to need those cathodes.
Okay, great. Alessandro, have you got any thoughts on the space in terms of the future of these ternary high nickel cathodes?
Yeah, indeed. And NMC, we can say now that NMC is a mature technology because it has been commercialized in 2004, and there was many investments for the production of such material. Then it's clear that its near future, NMC will be the most suitable cathode for electric vehicles due to this. But we can improve it because there are two chemistries. The first one, indeed, is to produce NMC with high content of nickel. Then it's good because we will increase the capacity, but we will decrease a little bit the capacity, but we will increase the safety of the cathode. And the second way is to develop lithium-rich cathode. In this case, you will increase the capacity, you will increase the voltage, but you have to face up an issue, which is the high irreversibility of this kind of cathode. Then there are many developments, but I think so that lithium-rich cathodes could be an interesting alternative to classical NMC or NMC with high content of nickel, because you will have high voltage and high capacity, and you could use the same production plant as the plant which was used to produce NMC electrode. It's more or less the same technologies, but you will change the formulation. And for me, for the near future, to go from high nickel material to high lithium material could be interesting. And in more future, we could change the technologies and think about lithium sulfur batteries, which are very interesting, especially if we combine these cathodes with lithium anode, lithium metal anode, and solid electrolyte to avoid any safety issues.
Okay, thank you. Before I move on to anodes, I just want to, Marie, have you got any further comments or on this topic? Or?
Well, I think that it's very important when we make these decisions, which technology or which chemistry we select, also to think about the business potential for recycling. Like, it has been kind of easy to find the financial motivation for cobalt-rich chemistry recycling, but when we start to have like lithium phosphates, or we start to have like lithium-rich lithium sulfur batteries, we also need to support by political actions then the recycling, which is not anymore kind of driven by the very, very highly valuable metals in the product.
So it actually needs a change in the policy settings in terms of how government think about it more than just for the value.
Or policy, or then kind of business, how to say, business ecosystem.
Yeah.
I think just, Jacques, sorry to interrupt. There's a lot of talk about lithium sulfur being much cheaper than other competing technologies, and I think the lithium metal is actually extraordinarily expensive. Yes, the cathode material is really cheap, but if you look at the processing cost of moving from carbonate to chloride and then the eutectic salt and then the energy that's required to electrowin lithium metal, it's pretty hard to buy lithium metal at the moment that's affordable. I don't know about most of you, but I almost go broke buying 10 meters of the stuff. So I honestly think that lithium sulfur, it will still have a huge amount of embedded value in it, because you can do current collective free ones, so you'll have still a huge amount of lithium still present. It may be still in the Li2S form, but that doesn't necessarily mean you cannot recover the lithium back out of the device. So I maybe Marduk has some thoughts on this, but I would imagine that the lithium sulfur chemistry should actually be potentially just as valuable to recycle, particularly if you look at the current price of lithium metal, which I think is running at about $115,000 a ton. So, you know, that whips nickel and other per ton values. So I don't think we should be suggesting that lithium sulfur is not going to be recyclable. I think it'll have just as much as inherent value, because you're going to need more lithium in there to support it in the first place.
Yeah, and I guess that's true also for a lot of the solid state, general solid state batteries, and
yeah, they're going to have a lot of embedded metal content in them. If you look at some of the stuff that's Solid Power, Solid Energy, these kind of companies that are putting together some of and also the new glass materials, which are being worked on by Toyota and others, they have a huge, some of them have germanium and all sorts of interesting glass chemistries in there with different metal elements in there that will definitely need to be recycled. So the question is how we're going to go about doing that. So the next generation of battery chemistries, I think, will still require pretty expensive inputs. And again, depending on scale and volume, you'll still possibly need to think about the recycling of those elements at a later date.
Okay. I've got one question here that came through from the audience, which asks, what are the panelists' thoughts regarding the possibility or desire to use ultra-fine nickel powder instead of nickel sulfate from a battery manufacturer process technology perspective? For those of you who have got any insight on that, would like to hear your thoughts. I don't have a specific comment from my side, but if you've got any thoughts on using ultra fine nickel powder. So I mean, what we've seen, Elon Musk has mentioned in his battery day of us working towards a sulfate-free process. Now there are various plasma processes and other processes to go sulfate-free. I guess maybe it would be interesting for those who knows anything about the sulfate-free options and the real commercial applicability of that. Would be great to hear that from any of you here. Just just raise your hand and I'll try and give you a chance to speak to that. I don't know who to go to on this one specifically, so just feel free to answer if you know anything. Otherwise, I'll just move on to the next topic.
I can't really answer that, Jacques, but I would assume, from the metallic nickel powder, you need to get it into an oxide form for these conventional nickel, cobalt, manganese type cathode materials. So there would have to be an alternative oxidation chemistry going on there. Yeah, I'd have to think about how practical that would be. But before you move to anodes, can I just offer a few thoughts on the nickel chemistry, because it's a subject Lithium Australia and VSPC are very invested in, and I guess our observation is the industry is working this out based on the fundamentals. So if you look at the cost of the cathode material per unit of energy you can store, nickel's relatively expensive compared to something like LFP. So it's at least 2-3 times the cost to have a nickel cathode material. You boil that down to about pack level, and the current prices for packs, LFP packs per kilowatt hour, are about 20% cheaper in the Chinese market at the moment. On cost, in terms of performance, certainly the nickel chemistries give you the energy density that you need to sort of serve the range anxiety of some EV markets, definitely. And then in terms of safety and life cycle, then the LFP offers that stability and greater cycle life. But we see the markets working this out. So nickel will be the dominant chemistry in those EVs that are serving markets that require, say, more than 500 or 600 kilometres in range. But there is a segment of the EV market where that range is not required. Tesla are just starting to serve that now. We see the reports. There's 7,000 vehicles just about to arrive in Europe, which we understand is the Model 3 with the LFP battery platform, range of about 400 k's, and that vehicle's 10% cheaper than the alternative with the nickel battery platform. So I think the industry's working it out. They're putting the right cathode material into the right product, and those that require energy density will go with the nickel and the improved nickel materials. LFP is making a bit of a resurgence in popularity. It's sort of the recognised chemistry now for most of the energy storage installations that are going on, sort of grid connected or smaller. And also the other sort of applications like the low speed electric vehicles, sort of forklifts, autonomous vehicles. Not as big a market as the sort of general EV market, but will become more important over time. And LFP is a good choice for that, where you want long service life, low total cost of ownership, reliability and safety.
I think it's very important that we, as globally, that we don't, let's say, overdo it in terms of using an over-spec'd battery for a particular application. That if we don't need an NMC chemistry, which that we actually that we make sure, because otherwise we're making use of a very scarce nickel and cobalt of scarce resources, and I think therefore choosing the right, that we don't use NMC chemistries for, let's say, stationary storage. But there's really very little reason to go for stationary storage with NMC. And there are other examples that like that, as you've mentioned, the short range applications, and so that in the end, for sustainable nickel and cobalt markets, I think it is important. Otherwise, it goes off the rails in terms of demand, and in the end, you get to a nickel demand which is actually drives prices to the point that vehicles are not affordable anymore, just because of that nickel consumption. So next question, Jerry, is around anodes, and again, it was something that was mentioned in the Tesla battery day around, there's silicon, which is like a sponge-like expandable type of high-performance anode. Within our CRC, and Adam is part of that team, is where we're looking at siliconized graphite anodes. And it's quite clear that, if we want to get the high performance out of cells, the higher voltages, then we have to focus on anodes that would match high performing cathodes, and then also the electrolytes to match all of those. So would be interesting to hear maybe Mardo, your thoughts on anodes, and this all silicon sponge-like type of structure that Elon Musk is referring to. Is it really such a big win, or is it just do you think it's like a bit of a market spin on this, or it would just be interesting to hear, what is the opportunity really in this space, and should we, we're invested for instance, as a CRC, we're invested into siliconized graphite systems, but not pure silicon at the moment, and we know that silicon expands and contracts a lot with the various charging discharging cycles, and leading to just the batteries can't really handle that in a conventional sense, although the new designs look as if it's, given this new sponge, expandable sponge thing, they do look at something that might be, more workable. But anyway, we'd love to hear your thoughts, for instance, on that.
Sure, yeah, but it was certainly an interesting announcement, in particular the way Elon Musk described the silicon. You may be aware that because of the expansion problem of the silicon, the startups and the literature, they tend to use nano-engineered silicon to help with accommodating the expansion. But what Elon Musk described is that they are actually using raw silicon material, the metallurgical grade silicon, which will turn out pretty cheap compared to the highly nano-engineered ones. And then, as he described it, they coat a elastic ion conducting layer to stabilize the silicon. Then they use a highly elastic binder to make the electrode. And looking at the process that he described and looking at the improvement that it brought to the specific energy of Tesla's battery, I would say they have kept their promise. Back in 2015, he said something around that they have around like 5-6% of silicon in the composition of their graphite anodes. And looking at these numbers, these improvements, I would say now they have around 10%. And I think that's pretty much it. With these sort of approaches using the non-battery grade silicon, 10% is actually pretty good. In particular, because in addition to the improvement, 20% in the driving range, which is pretty exciting, I'd say. They're also talking about 5% reduction in the battery price, which is again pretty good, because not that an all silicon anode is not possible. It is. There is another company, Amprius, which is actually located very close to Tesla, and they do use an all silicon anode, silicon nanowires. They're actually a spin-off from Stanford University. And the sort of performances that they are reporting, and they're reporting it at a commercial level, is basically what you are expecting from an exciting all silicon anode. Energy densities at a range of up to 500 watt-hours per kg, up to 1200 watt-hours per liter, massive power density improvements, and so on. But then as clever as the design is, I assume they're facing severe challenges ahead of a scale-up, because they're going to have to grow these nanowires on a substrate, and they're obviously limited by the growth rate of the nanowires. And then again, it's an all silicon anode. It's going to be accompanied with a massive, I would say, loss of capacity right after the first cycle, which they're going to have to compensate with a pre-lithiation process. Again, it's doable on a smaller scale, but I'm not aware of any large manufacturers that would be able to do that at a larger scale. So I guess what Tesla has achieved is pretty good, and that's probably pretty much it with that approach. Yeah.
So is it essentially a scale-up challenge, Adam? I think some of your thoughts on is it basically, you know, scale up that really kills it, rather than I mean, it can be shown, as we see, on a small scale, but you know, when we do industrial scales, we want to implement these things in electric vehicles. You know, to what extent can we make it real at a large scale?
I suppose I have to be a bit careful what I say here, but Tesla had bought a number of startup companies in recent times, so some of the stuff that they've bought I've actually been aware of, so I can say that they're going to get a lot further down the road than what's been published based on what I've seen. But the part of the problem is what you point out, Jacques, is basically the scale up problem. So having seen a few of these companies, the same problem that Marduk talked about with Amprius is the same problem that a little UK company called Nexion had years ago. They were making what they called hedgehog silicon. So it was basically a particle, and they had it look like spines, and their whole theory was that volumetric change in the spines was compensated if they could control the degree of lithiation. And they tried to scale this up into a pilot plant, which I had the joy of seeing, and it didn't work. They just could not get, they could make the compounds, but they could not get the cycle life and performance. And plus the SEI challenge is just massive. The reactivity of the electrolytes on those surfaces is just unparalleled. So you've got a constantly forming and breaking SEI because of this volumetric change, which dries it out the cell and kills it off. So yeah, you can get away with these things in a coin cell because you can add outrageous amounts of electrolyte to them, and such that you've got basically almost a a bottomless reservoir of electrolyte. But as soon as you get to a pouch cell where you're trying to control your NAM and PAM ratios, your electrolyte ratios to maximize your energy density, then that's when that's when trouble really hits. And some of that scale up is really where the challenge is, because you're trying to eke out every last little bit of energy density. So you try, everything is balanced on the ragged edge to get to that point. So at the moment, as Marduk points out, I think it's about 5 to 6% is silicon in pretty much every commercial anode you'll buy today. And again, all the companies want to go higher. But the question now, of course, is that volumetric change on charge and discharge just puts so much strain in the electrodes and the like. It makes life very difficult. So do I see a day of 100% silicon? No. But do I see a 50% day? Absolutely. I think that's absolutely doable.
And if we look at your like the 10 to 20% target range of silicon graphite, do we see if we target that in Australia, for instance, that is something that will last us the next decade, or we will be getting out of runway on that technology fairly soon?
No, I don't think so. I think that if you look at the time scale of battery development and you look at the amount of effort and time that has to go into validate cell chemistries and the like, as you know, once you come up with a formulation, you got to turn it into Sarge cells. You got to do 1,000 of them, safety testing, calendar testing, all of this stuff. 20%, if you can get that and validate that, that's going to be good for quite a good lot of time. But the problem is there's any number of precocious startups which will be trying to up that every minute. So yeah, there's always going to be that push, and I think that's that technological push that is allowed to see the massive improvements that we see in battery technologies today.
Okay, great. Andrew, I just want on your side, I mean, when we look at batteries and the graphite that actually that goes, if you produce graphite in a mine, you get $500 a metric ton, for instance. When you get to a siliconized, nanosized and siliconized material in the anode, that same graphite goes anything between $10,000 and $20,000 a ton, depending on various attributes. To what extent would EnviroStream look at actually anode material recovery? Is there any sense in that? Just given the huge price difference between manufactured graphite versus graphite sourced, again, primary graphite.
Yeah, this has been an interesting topic for us. Everyone thinks graphite just floats off and we can easily separate it, and we've done some work with some universities and different liquids and different froth flotation and really tried to look at it. But I think it was at a conference at CSIRO where we had people talking silicon wraps the carbon and a heat shock type of, I'm just going, I don't know. It's hard enough to get the binder off this stuff. Like, I don't want any other silicon in my graphite and all these things. So it really becomes a problem. We try and chase the cathode material separate to the anode, but we can't get it clean yet. And it will take more processing, which takes more volume because of the cost of that processing. So if we then dirty the graphite, we've got 50% of that material. We look at silicon as a impurity into the graphite because we lose that market. And sometimes the market, the best for us for graphite might be a lubrication market or a reuse market there, because it's not easy to clean that up to battery grade again. So this is, as a recycling company, what happens when people mix everything together and to make this much more economic, or not a longer lasting battery or a higher energy density. I don't want to see 500 watt hour per kilo batteries going in dangerous goods transport. It's hard enough to store large power tool batteries that they're bringing into mowers these days, 56 volt, bigger. How do you drop them off safely? How do you collect them safely? This is all the things that I look at. It might be a bit of a it's a different approach. That's all it is. We're all in the same space, but it is exciting. All of this talk and development, it's really exciting for all sides, but that definitely complicates our anode recovery.
Yeah. Okay. Yeah. Just looking at the time and so on, we've got about another 12 minutes to deal with two questions. So I'm going to field these two questions quickly. The one is on what opportunity is there for Australian electrolyte manufacture and niche cell production. So this is an interesting question. Should Australia, I mean, there's I guess an easier case to be made for cathode materials. For anode materials, we can probably make the case as well. I guess the question is then second, you know, should electrolyte manufacture ever feature? And if so, you know, what would be the nature of that? And then the follow-on of that is, you know, niche cell production. Do you actually see a future for that in Australia? So this is a bit of an Australian centered question. So apologies to my European colleagues, but would like to hear maybe Jose and then Adam would like to hear and Amado.
Maybe I get started. The niche cell, for example, it could be interpreted in various ways. But for example, if a particular electric appliance is produced in Australia that depends on a particular battery performance, perhaps there is a case to combine the two into a development of the product. An example could be a particular vehicle model requires a particular format of pack and all that, and that could become a niche type of style of modules and packs. The other interpretation could be for particular environments. If we have strong demand for a very hot railway in Australia or so, maybe we need to have specialized high temperature performance packs that other countries may not be so inclined to develop, but maybe it's considered a social necessity or a business necessity in Australia. I think there might be cases where, yeah, it might be good to contemplate, probably not in their own to be an export product, but maybe it's more like to satisfy a particular local need, I think.
Okay, thanks. Adam.
Yeah, this is actually so I obviously wear two hats at the moment because I'm involved with Energy Renaissance. I'm currently working with them as their R&D advisor a day a week, so I'm changing hats here. One of my challenges as part of that role is actually to help them to develop an Australian supply chain of all the materials required to actually transition them from an imported materials into local supply chains. And one of the things that is starkly obvious very early in the piece is our inability to make electrolytes to support the cell manufacturing business that they're going to have in their Tomago plant. So at the moment, that journey is beginning around how can we have a local sovereign supply of electrolyte in order to support the factory that will be built there. And that's the second aspect of that is obviously Energy Renaissance has announced they'll be making a 5.3 gigawatt hour battery plant, which will be located at Tomago, I've got to get it right, otherwise the locals will kill me, in just outside Newcastle there in New South Wales. So, and that's going to supply a whole range of different products, which are branded under the Renaissance One website that you can see there. So obviously I'm heavily involved in the design and the development of those products with them. So we do see an opportunity here to supply electrolyte, and it's a pretty, if you do your maths on 5.3 gigawatt hours, it's a pretty eye-watering amount of electrolyte that needs to be produced. But I don't see us producing lithium PF6, for instance. That just would not be economically sensible, nor probably would we produce carbonate carbonate solvents unless someone else was doing that for another application. But there's definitely the opportunity to do formulation, and then there's also the customization again, as Jose pointed out, depending on where those products are used and how we want to design the battery packs and how we want to, if we want to improve the energy density and remove other aspects, we may be able to do things with the electrolyte in order to make the product perform better without all the ancillary equipment that sometimes battery packs need. So definitely opportunities. How they look in the years to come, I'm not sure, but we're going to go and test the market and see who's keen.
Yeah, thanks. Yeah, I think we've got CRC, for instance, we've got one manufacturer of ionic liquids. Not necessarily that's the option to go by, but it's so we've got Electrolyte project and one company, Solve Ionic, which is a French company, of Toulouse. They're involved with us, and so Mado, I think if you've got any comments on this space and in terms of the electrolyte side of things, you know, do you think we should actually get into this space? Is there something that Australia should do in a niche sense in terms of either electrolyte manufacture and or cell manufacture? What would be your view?
Yeah, well, I guess as Professor Talbot mentioned in his talk in the morning, there is great evidence, there exists great evidence that we do have the potential to do way more than just mining for the battery minerals. I'm not saying that we should jump into the final stream of the battery supply chain, like making and assembling battery packs and so on, but we can do a lot more in the second and third stream, like refining the battery materials and electrochemical production in particular, like electrode and electrolyte making and so on. There is obviously way more great value in those streams.
Okay, thank you very much. I think we've got 5 minutes left. I just want to quickly touch upon recycling. Marie, I'm going to get back to you as well, because you're in Finland, you've got quite a big focus on recycling. Andrew, I'll get to you, and Alexander, I think on your side as well on recycling. In each of your respective countries, whether it's in Australia or Finland or France, and so your perspective as to, you know, firstly, how would you see the recycling industry positioning itself for the diversity of batteries coming their way in the future? Is it a matter of only dealing with internal in-country recycling, or basically importing cells from other countries to add economy of scale? I guess is a question. And then the other thing is, you know, as Andrew Mckenzie earlier mentioned, often you get all these batteries and they're all jumbled together, different types. You'll have zinc alkaline batteries thrown in just for the mix as well. So it's not an idealized situation. Recycling is a very difficult space because of the diversity of chemistries. You know, we'll have, even in lithium ion, we'll have LFP and various NMC chemistries, NCA chemistries. We'll have different types of electrolytes, different types of anodes, and then you'll also have, you know, a range of other, you know, might have lithium sulfur chemistries or other things coming in the future, solid state electrolyte chemistries and so on. So recycling is actually in a sense a bit of a nightmare because you just have this enormous diversity, and that diversity is not only, it's dynamic in itself, because what you get this month in terms of the ratio of this type of battery to that type of battery is different to what you're going to get next month. So it's an incredibly complex space, and I would be keen to just hear how you in each of your countries would like to see this space evolving, and how do we get to what is really a practical recycling industry? Marie, haven't heard you for a while, and Andrew, I'll end up with you if you don't mind. So maybe first in Finland, how do you see the recycling industry in Finland, and do you see it as a service for the rest of Europe, or only something for in-country recycling?
Thank you, Jack. Maybe I would like to also mention in this stage that we have a huge batch circle project ongoing, or battery metals ecosystem in Finland, which ALTA University and myself, I'm leading. And there we focus very much on this, that how do we recycle batteries, how do we actually integrate those also to primary production? And regarding to diversity, the issue in Finnish industry is that at the moment, it's much harder when we have so much of portable batteries, portable different devices, and very, very much manual dismantling. We do import to Finland batteries also regardless of this diversity, and treat that mechanically, and then sell the concentrates to different primary or secondary producers. In future, situation will be different. So EV batteries will make it easier, as you can, for example, coat the chemistries inside the EV battery packs, and also they are still more similar with each others compared to the portable batteries. And we have a strategy to be a very strong player in Europe with the recycling operators because of strong background in primary production. So we do have the knowledge and we have the infrastructure. And the status at the moment is that several primary plants are treating the fractions of battery waste, but Fortum, actually, which is an energy company, has bought a hydrometallurgical treatment company, and they have now the whole chain from the mechanical dismantling to the up to the recycling, and they are also located in this Harjavalta area where they can integrate to the battery value chain in the up to the battery salts. And we would like to see also the import, so definitely not to be like in-country effort, but we would like to see import also of raw materials like concentrates to finish production with the benefit of we producing at low CO2 impact, so recovering more and also focusing on CO2 low processing of the batteries. However, the regulations for transferring of the the battery waste across the borders is a bit challenged and should be also addressed in Europe.
Okay, thanks. Alexander, thank you very much. Marie, Alexander, if you some of your thoughts on in France and in terms of the positioning for recycling and how they think about recycling. Firstly, would they only treat in-country material? How do you deal with the diversity of batteries, and then would you import materials? I guess those are the questions around recycling.
Okay, I would say that in Europe and especially in France, producer may be in charge of recycling of their own product. Then it means that they have to organize the recycling value chain, the recycling chain. That's the regulation. It means that today, indeed, you're right, there is a huge diversity of technologies. Then it's not so easy to perform recycling when you have different technologies. But what we can observe is that today we have the formation of alliance, of collaborations between recycling industry and car manufacturer, in the case of EVs. Then it means that thanks to such kind of alliance, we will reduce the diversity, the huge diversity of technologies to process, and that's good because it will simplify, it will get easier the recycling process. Then it means it's not so easy to have a good idea about what will be the streams of spent batteries from which countries. Probably from inside Europe, because car manufacturers are not located only in France or only in one country, but in many countries. And we can imagine that we could have streams from different European countries in order to use this kind of alliance between car manufacturers and recycling processes. Mm-hmm. That's my opinion.
Yeah, thank you. That's valuable. Thank you. Andrew, to wrap up on your side, I think after Andrew, I'll just give a, if you've got anything else that we wanted to before we end, just put your hand up and I'll deal with that. But otherwise, Andrew, from your side, what are your views?
Yeah, thanks, Jacques. I know we're running close to time, so just quickly, I think the length of your question explained the complexity of this problem. But definitely, transport is a big issue, and being a country that signs up to Basel conventions and the OECD rules around battery movements, I think that's the most complicated part at the moment. It is definitely the regulation of importing. We've got issues with supply quantities in Australia if we only look after our own. The problem is you build a business, you work out this, you've got the technology to do it. If you can't get supply, you won't succeed. So we really are focused that, but import is very difficult. Same as if we would like to export to Finland, we have to go through so many ports and so many different regulations to get there. So moving batteries around is the biggest challenge. I think while we see chemistry changes and all that, we do have a solid supply of you know, a few chemistries, so that underpins the business. But like Adam said, lithium metal, but how do you recycle it? How do you do it? You know, there's another range of, but hence your question was a long one, because it's another chat for another day for sure.
No, we probably need you can have a whole conference around this only.
We don't want everyone to know about it though, so we'll keep that short.
I see. Yeah, thank you very much. I see Mike Vasey had to go. I would like to use this opportunity again to thank all the panelists and all of the remote audience out there that are watching this this panel. I hope you had some insights coming out of this panel discussion. Thank you very much. Thanks for your time and preparing and making yourself available for this panel discussion. From my side, I just want to say thank you and goodbye.
Thanks very much.
Yes.